Hi guys, so welcome to UXit, online learning platform. You can find us at uxit.com. And our new batches are going to start from 1st of May for NET, GATE, and JAM. Of course, they are all going to be in physics. And then we have JEE and NEET too. So they are starting from again on the 1st of May, right? So the students are welcome to join these two things that are the important announcement to make. You can visit our website and you can find out more details. So right now the idea is to give you some glimpse of what we are learning right now. We are looking for the course of statistical mechanics, right? That's what is running on in our things. And statistical mechanics, we have very much like we want to interpret the statistical mechanics from the fundamentals point of views of thermodynamics, that is from the second law of thermodynamics. Right. So we are looking into the second law and the definition. So today's class is very much like a kind of giving you the glimpse of what does statistical mechanics and how it has been formulated long ago by the pioneers of the field. And once you do that, you will see that a lot of questions are going to come out in your examinations, especially the statements about entropy in your NET examinations and GATE examinations. Of course, we are going to look at the problems in separate sessions, and the videos will also be soon be available for you. And but today's class is more like fundamental to give you a glimpse, which these concepts are pretty important, I would say, for your interviews and for your whenever you are going to clarify your GRFs and your JEST or other examination GATE, and you are going to prepare for PhD entrance examinations in all institutes in India and abroad. All these they are very fundamental concepts, I would say. Each one of us should know about it, right? So let's look at the second law of thermodynamics. Look, when we read statistical mechanics, we just have been thrown into the concepts of probabilities and partition functions and calculation of partition functions, but no one has ever taught us that how come these things are connected with the thermodynamics, how the statistical mechanics is very much originated from the basic aspects of thermodynamics. That's what the idea is. And second law is very much something like that. We should really ponder on it, right? That's the idea. So, I mean, this is basically the ongoing course, and we have seen in the very much the available one video, which is very much fundamental on statistical mechanics, is available on our YouTube channel. You can go and take a look on that. And we have seen that what are the basic aspects of second law of thermodynamics, and especially the let's say Kelvin statements. So Kelvin statement, that's what we have seen. And the statement is very much associated with the idea of heat engines. So we will look at what these heat engines are. So I said you consider a setup of some sort of setup. Let's say we design setup, and setup is something like this. I have a system, and the system is having a piston, and the piston is somewhere merged in the system, and let's say we fill the gas up to this level, and the system is insulated from the surrounding and maintain its temperature, let's say 0°C. Let's say this is my step A, right? Now what I do, I just put some weight on this piston, right? And I arrive in a state, let's say state called B. And when we put the weight, the natural idea would be that the system is going to compress, right? And then that gas is going to compress again here, right? So this is again your system C. Now, what I do, I just construct again a third system, and the third state is again going to construct it by something like connecting it to some temperature, which is very much high to the previous one, right? And what will happen now? The system, there will be temperature gradient and there will be the flow of heat, right? Because this end is connected to the higher side, right? And the heat, when the heat will flow, this piston will lift up and the weight is going to lift up here, and there will be expansion of it, right? And you know that for this, for when can I say this to be an engine, right? Because engine has a property that it has to be operated between back and forth scenario, right? So to operate this as a back and forth, I again have to maintain my, I again have to go back to my initial state, which was my 0°C state, and I have to cool down system to this state, right? And then again, I can come back to my initial state, right? So in doing all these steps, like steps A to step, let's say D, right? I have injected some heat into the system, and you see that it was 0°C. As soon as I go from state, let's say A to C, right? I injected some amount of heat into the system, and the injection is lifting the weight into the system, right? So you are putting the heat in the system and you are getting work out of it, right? That's the idea, is something happening. So there is a optimal way of doing that, right? You are putting the heat into the system and getting out the work out of it, right? There should be some optimal way. So what could be the optimal way, right? That's the basic question that you can ask to yourself. What could be the optimal way? And the number one is something like, you can say that the all amount of heat that I have put in the system and the same amount of work I can get out of it, right? But you see, that's where the basic aspects of the second law is come. Like you can't just convert all amount of heat into work, right? Just you. So first thing is you cannot convert, right? All heat. Sorry. So I have to my pen. So you cannot convert all heat into work, right? So there could be no engine which, while operating in cycles, the sole effect of which is pumping energy from one reservoir and converting into heat completely, right? The sole effect of the engine can't be that you put all heat and convert into work. There should always be some mismatch, and this really puts a limit that how much work you can get. So like it will put some limit, right? It will put some limit that how much work you can get from an engine, or let's say heat engine, right? And then the famous engine, you know, that's basically your ideal Carnot engine, which is basically have been named in the name of the famous engineer Sadi Carnot, and basically he was very much interested in the efficiencies of heat engine, who operates between the two temperature scales, right? Let's say engine is operating between, let's say, T1 and T2, right? Let's say T1 and T2, and then there is some substance which is filling here, right? So let's say engine which is operating between two temperature difference, let's say T1 and T2, what will be the efficiency of such an engine? And he found that the efficiency turns out to be something like function of some, temperature. So these are the basic formulas which will be derived in the next lecture, in the coming slides. So, but right now we are very much interested into defining the basic second law of thermodynamics, and we have defined the Kelvin statement that there's a limit of work done that you can get out of the heat, right? So this is a one statement of second law of thermodynamics. So first statements. So let me make the first statement, and that's also called Kelvin statements. So that's also called Kelvin statement, and the statement is And the statement is, it is impossible to convert heat completely into work, right? That's what you have seen. It's impossible to convert heat completely into work, right? So there's an so this is one statement. Now let's look at the second statement. Second statement, and that's called what? Clausius statement. So let's look at this statement. This is a more kind of statement which can you really correlate with yourself. For example, I will draw some pictures which will help you to understand what the statement is, right? Now consider a scenario where you have one system at, let's say, temperature T1 100 degrees Celsius, and one system which has a temperature, let's say, 0 degrees Celsius. Right? So now, if there is a, you see, there are two system, I mean, or the part of same system which have been maintained, and let's say there's on a slight different temperatures. So the natural aspects, you will see that there will be the flow of heat from one to another, and they are going to equilibrate, and there will be the common temperature, which is going to be something like this, right? So, and similar way, if you consider, I consider a chamber, let's say a gas chamber, and I divide into two halves. Let's say the gas is filled in the half of the half. Now I remove the partition. Then a natural way to imagine that the gas will be expanded, something like that, right? There could be one more scenario, like where the two partition will contain the different sort of particles, right? Something like this. And then you again remove this partition, and you remove this partition, and you will again see that there should be mixing of all sort of, right? So you see these sort of, let's say, if I define this as a, this is a B, this is a C, there's a natural way of proceedings, and the natural way is that all processes have one thing in common, and that they proceed simultaneously in the one direction, right? There is no reverse way of proceeding it, right? So you see that like temperature flows, heat flows from a high temperature. There's a flow of heat from high temperature to low temperature. When there's a concentration gradient, there's a flow of particle from the higher gradient to the lower side, as you can see in the figure B, right? So there are processes where basically there is a unidirectional flow, right? Unidirectional flow, right? So on the time scale, let's say this is my time, and this unidirectional flow I can define with a quantity, and for the sake I will call this quantity as entropy. So this is the first definition where entropy came into picture, and where we have just Clausius introduced the definition of entropy, which is associated with the direction of flow. Now, entropy has, this is a very fundamental aspects of looking entropy, and it's the first ever formulation of entropy. But there's a very atomistic kind of definition of entropy, which is basically a Boltzmann definition of entropy. So we will look into those aspects in more detail in our next lecture. So this lecture is, we are going to wind things over here right now by giving you just the two equal statements of Kelvin's and Clausius. And Clausius definition, you have seen that there's a unique directional flow associated with the on a time scale associated with the quantity which changes in these directions, called the entropy. So that's the way nature proceeds. Nature proceeds from order to disorder, right? So that's the basic idea of defining your entropy. So thank you for joining for today's class. Stay tuned for the next lecture. Thank you, and do visit our website.